This is experiment 7 of Make Electronics, second edition by Charles Platt, investigating a relay. We'll start out by checking our battery voltage. Again, voltmeter on the voltage mode, 20 volt maximum range. And once we're done doing that, get together equipment. We need a couple of 9 volt DC relays. They are little black boxes with 8 leads sticking out of the bottom. And we also need a push button switch as well as some alligator clip leads. Finally, you're going to need a utility knife and a warning. This experiment can potentially cause injury by misuse of the utility knife. So please be careful. We'll give you some tips on proper use of it in a bit. So there's a relay. You will be needing 2, potentially. One of them we hope survives. We're not sure. I should say a 9 volt relay, and when you flip it upside down, you'll see a pattern of pins as shown in the figure in the upper left hand corner. And it's important to notice that there are 6 pins clustered towards one end and only 2 on the others. And we're going to start by hooking the relay up using just the 2 pins on the one end. Now, in general, you can hook voltages up either direction on the inputs of a relay. There are some relays that might be specific, so if you're not using one of the ones from the kit, you should be willing to try some different directions. Okay. It's a little bit tricky to make sure that your probes don't touch each other and short out the battery. You know, that's a disaster, especially with a 9 volt battery. So as you're hooking onto the leads of the relay, be careful to keep the little alligator clips separated so that they aren't touching. Similarly, you might want to bend the leads apart a little bit on the push button or the tactile switch to make sure that those leads don't touch either. You want to complete the flow of current through the circuit only when you touch the switch. Let's go ahead and spread those legs out a little bit, and again, be careful to get good separation between your probes on the relay. All right, we should be ready to go. When we press the button, we should send current through the relay, and what we'll be looking for is a clicking noise. And to change the continuity on the meter. So one of the tricks I'm going to do, because I'm already started to run out of hands for these experiments, is use an extra set of alligator clips, if available, to clip from the voltage probes over to the area I want to examine. So rather than holding the probes up to the relay, I'm going to clip them on. And now I'm going to use continuity mode. Remember, in continuity mode, it beeps when the circuit is completed. And shows a resistance going to 0. So that's what you want to demonstrate first with the relay. If you clip to the second port instead of the third, the second terminal instead of the third, you'll find that the switch is normally closed instead of normally open. And if you cross from the left to the right side, you should always find that it's open regardless of when you press the relay. That clicking sound is normal, and it has to do with how the relay works. Become more obvious why it clicks when you take it apart. So please pay attention to the circuit diagram and move around, checking what happens on those upper 6 leads when you press the button. Which ones are normally open, which ones are normally closed, and attempt to understand what's going on by looking at the circuit diagram. And this looks like a double pole double throw switch, which is operated by the push button plus battery. If I were to disconnect the power coming from the battery, this switch would remain in the state it's normally on, either off or on, depending which of the pins you're attached to. Alright, let's take the relay apart. And this is going to involve a knife. Now, if you look at that scar on my hand, you see I've had a run-in or two with a knife or scissors in the past. So don't be like me. Always cut away from your fingers when you are trying to open the relay. The textbook has got several good diagrams, but the basic idea is to slice off the corners and then peel back the top to reveal what's inside of the relay. Take your time and be careful. Eventually you get to the point where you can kind of make out what's going on the inside. You may have bent some of the leads, so make sure you get those back nice and straight. And then hook up your relay again, this time without the multimeter, but just observe what happens when you throw the switch. What you see is that running current through those bottom two leads pulls up, due to an electromagnet, pulls up the switch. So there's a switch activating a switch. Now, why would you want such a thing? Well, the idea is that a relay allows you to control a large current or large voltage, that is a high power circuit, using a much smaller signal. So we have a 9-volt battery which is powering this relay, but in fact this relay is large enough to practically switch wall current. And so it's a very good way to use signal electronics, the type of electronics that we primarily study in this class, to make bigger things happen. Turn on lights, ovens, air conditioners, and so forth. Let's take a moment and look at the diagram showing the inside of these relays as drawn by the author to discuss what's going on and how that really works. You're probably familiar with the phenomenon of electromagnetism, as demonstrated the figure at the bottom here, where if you wrap a coil of wire around a cylinder, particularly one made of material containing iron, you will be able to pass a current through that wire and pick up small objects like a paper clip, sort of like the big magnets, electromagnets we imagine used in junkyards for sorting out metal. Well, that's exactly what's happening in the lower part of the relay in each figure. The push button allows current to flow through a coil. Those are the bottom two contacts. And when that current flows through, it creates a magnetic field that draws down the switch that's closest to the magnet and pushes it up then and away on the other side of the lever, contacting the other contacts. So that switch, that small vibrating up and down or that clicking, is the contacts moving in response to the applied magnetic field generated by the current running through the bottom coil. In the next part of the video today, we're going to look at something that's not in the textbook, but does follow along with it quite well, which is using a circuit simulator. The website is given in the video or in the comments. It comes up with that very complex looking circuit, but I'd like you to clear it by circuit, draw circuit, and then go and let's add some components. We're going to start with doing the simple double toggle switch from last time. So let's add a voltage source. You can press lowercase v or find in the menu, and you draw with your mouse on the screen. We're going to make essentially a circuit diagram that actually simulates what's going on inside our circuits. We'll then apply this to the relay on the homework. And when you double click on an element, it'll bring up a menu which will allow you to flip it upside down. So we'll put our ground towards the bottom. We'll talk a little bit more about voltage in the simulation in a bit. And then you can add wires, or what we've been dealing with so far in this class, which are passive components. That would include the single pole double throw switch, for instance. So let's add a couple of those in to represent our toggle switches. You stretch your mouse out to make the switch of a particular size. Notice the 3 contacts, middle, top, and bottom. We need, of course, a second switch, so we'll put that in as well. And we're just going to duplicate the circuit that we had in experiment 6 as a demonstration. Let's put in some wire, type lowercase w, or find it on the menu. And just draw, and it should snap into place between contacts pretty nice and easy. So remember, the outer 2 contacts in our original configuration were connected, so I'll put those in here. Just like drawing a circuit diagram by hand, try to keep straight lines and avoid crossing wires where possible for clarity. We'll connect the inner 2 contacts between the 2 toggle switches as well. Now, to complete our circuit, so remember the next thing that was in there was a LED. That should be under outputs. So yes, we can just add an LED. And a little symbol should pop up when we draw it on the screen. And in fact, if we're clever, we can start at the 1 contact and just pull it down. There's our LED symbol. Make it a size we're happy with it. Notice the LED is currently off. So there's no current flowing through. That's what the empty circle indicates. Now we need to add a resistor. That's lowercase r. Just draw that resistor. It always comes up as 1 kilo ohm. By default, by double clicking on the resistor, we bring up a menu and we can change the resistance. I think we used 470 in experiment 6. We'll just make it a 470 ohm resistor. Now if you need to move an element around, you hover over it and press the space bar to move it. Otherwise, clicking will just draw more of the same component. So go back, add wires, complete our circuits to the ground terminal, and there we go. Now, notice how we see some little charges appear and then disappear when we hit the run stop button. There are some issues with using the simulation regarding the polarity of voltages. First of all, right now just checking out the switches. I click on a switch to throw it. It's pretty clear. Hover over an element to see what it is, in case the diode's in there but is off. And you'll notice I'm actually not getting any current flowing through my circuit. So you have to sometimes play a little bit around and switch your terminals, and often in this particular simulation, for some reason, you often have to reverse the voltages as well. So I'm going to go in and flip back my battery, send it up to 9 volts first of all, just like our 9-volt battery. Still not working, so you just have to feel free to play around a little bit, check all your connections, flip your switches. What's going on? Well, let's make it minus 9 volts. That usually is the trick here in the simulation. Everything seems okay. Oh, I think we've got the lead switched on our battery, so yep. I'm showing you me struggling here on purpose to show you should feel free just to mess around with it. Okay, there we go. We switched the leads. The ground is at the bottom. We set to a minus 9 voltage difference, and it looks like now our LED is on and glowing red. We should be able to go around and throw our switches in the original configuration. Now, it turns off when we throw a switch, back on when we click to open it, off, on. Let's go to the other switch. Every time we touch a switch in this configuration, it should change the state of the LED, and that seems to be what it does. So a couple reminders again, mess with the polarity and the direction of your batteries, especially if an LED in the circuit, to get it to run. and remember to hit that run stop button. But otherwise, it's an absolutely fantastic simulation. It'll handle basically every circuit we're going to design in the entire 3-course sequence. So today's homework actually is to play with this simulation a little bit. First, I'll go back and into that online circuit simulator and draw up and simulate the 2 circuits that you did for experiment 6. That is the toggle switch where both had to be in on or left position, say, to turn on the LED, or both had to be in the off position, say, to turn off the LED. Put a screenshot of each simulation in your logbook, and then go and find and build up in the simulation that relay circuit, just one which toggles a relay in figure 2-49. The relay and push button are both found under passive components. Please put a screenshot of that in your logbook as well. If your relay is still functioning, hang on to it, otherwise get rid of your relay. We'll be using a functioning relay quite a lot in the coming couple of lessons.